The first presentation is a collaboration of Spain and Brazil mathematicians. So the keyword of this session is the Choque integral. So in order to be first speaker, the place is yours.
Thank you. Hello, my name is Joaquin. I'm from Public University of Navarra, and my talk is about DF chocolate in Spanish function. And this talk is practical, and I'm going to show two applications: image reduction and pooling is CNN. The plan is this one. First of all, we are going to talk about the motivations, why average and mean pooling are not enough. The second part, we will show the operator that we define in the paper. And after that, we're going to talk about the applications, image reduction and CNN pooling. And at the end, we'll talk about the conclusions and next steps. Why we try to do this job? Because local aggregation is everywhere. For example, in image reduction, we take we shift windows from, for example, 2 by 2 pixels, and we aggregate them to create 1 pixel. And for in pooling layers of the convolutional neural networks, we take the windows of feature maps, and in the pooling process, we combine them to create one feature. But standard choices that it's more commonly used, like maximum and average, are too rigid. For example, maximum it's very sensitive to outliers and try to keep peaks, and average it's usually smooth too much and may remove small details or edges. In other cases, for example, traditional chocolate integral could be a good option, but you have to compute the FSTA measure, and it could be very computational expensive. That's why we are looking for another option, which is more flexible and interpretable than maximum and average, and it's also easy to compute rather than the chocolate traditional integral. And that's why our formula is the DF chocolate. I'm not gonna go very deep in theory, and I'm gonna explain simply what we use. This formula has 3 main steps. The first one, we order values from the lower one to the largest. The second one, we calculate the gap about between each value with consecutive value, and at the end we multiply that gap, those gaps with fusion, and we sum them. For example, if we have a 2 by 2 window of pixels, the calculation is start with the lower value. After that, we compute the 3 gaps between the second value and the first one, the third and the second, and at the end, the largest value and the third one. Each value we multiply with a different function. The main key of this function is that we could use different functions to each gap. That allows us to have a more sorry. Well, that's an example. And the key of this function is that the online computation of the function it's very cheap. But if you want to find the best sequence of these functions, it could be very expensive. For example, for a window size of 2, we have 4 values. With these 4 values, we choose 11 aggregation operators from 3 constants, the 0, 0.5, and 1, 5 functions, the mean, the median, the minimum, and the maximum, the product, and 3 or 1 variants. If we take that information, we have 1,300 sequences. Some people may ask, why don't you use a window by 3 by 3 pixels? And the is that if to find the best F sequence, we do an exhaustive of search. And if we use a 3 by 3 pixels, we have 9 values. Well, so 9 values with 11 candidates. We have 11 power at 8 values. That gives us 200 million sequences. If we try to study that with a data set of images and 5 noises, well, with 5 noises, it will last. That's when we use the 22 pixels. So in the first application, that is image reduction, what we're going to try is to find the best combination of that F functions to next use it in the convolutional learners. So in this application, we use the dataset BSDX 500 in grayscale, normalized to 0.1. We use 5 noise cases to study the robustness of each sequence, and we use windows by 2 by 2 pixels. And the evaluation is we use a similarity measure that means a pixel-wise similarity. The main idea of this application is we take the image, we reduce it, then we rescale to the original shape with a linear interpolation, and we compare these two images with the similarity measure to analyze what is the performance of the F sequence. So the results of the sequence gives us that the best combination is the constant 1, constant 0.5, and constant 0. Here you have the 5 best combinations, and you can see one pattern that works the best. This is that in the first position, we have a constant 1. In the last position, we have a constant 0. And in the second position, you have some different functions. For example, here you have a heat map or how each function works in each position. And you can see the same pattern that in the first position, the best one is the first constant. In the second position, the best one is the zero constant. And in the middle, it depends on the function. It's very similar. And for example, in the top 50 sequences, here you have a 3 diagrams that in each row, it counts the number of appearance of that of each function in the top 50 in each position and in the top 50 sequences. And as you can see as the same as the previous diagrams, that in the first position, it wins the first constant. In the last position, the best one is the single constant. And in the middle, you have a different functions. And here you have a diagram that shows more or less how the function transition between each function. It's more. And at the end of one will have the best gift token inspired with the best sequences. We compare that that operation with the 3 that that usually the people usually use: the maximum, the average, and the chocolate. As we can see, the F chocolate inspired wins in the noise-free and salt and pepper noises, rather than the average wins in the Gaussian pulsion spectrum. The main difference is that the average wins, but our function is very close to it. Would be a good option in the pooling or in the image reduction processes. And here we have the second application. We have now we have the 5th best sequences that these ones. We are going to apply them to a pooling layer in the convolutional neural network. So because of these functions usually works in the 0-1 interval, but in the neural networks we have real values. So first of all, in the pooling layers, we have to map the feature map into a 0-1 interval, and after that we will take back that map in the original range. So we are using that monotony, and in our implementation we use the min-max functions. In this convolutional neural experiment, we study three architectures: LeNet, BGG, and DenseNet. We use it in four datasets: Cypher10, FastMinist, Minist, and MNIST letter. And of each combination, we train 5 different models, and then we report the mean and the standard deviation accuracy. So as I said, we train models with these pooling layers, the 5 best of the image reduction, and in the maximum, average, and chocolate traditional to have a baseline ratio. Here are the results. As you can see, well, it's not very clear, but as you can see, our functions are very similar, but in the average, it's still the best option in this convolutional neural network. But our scores are very similar to that average pooling layer. And for example, we observe that the fixed sequence 1, 0.5, and 0 is the best, for example, in DenseNet and FastMinist, and MNIST and MNIST letter. So what we have to remember is that we have a position-aware design, that we can vary different F sequence to generate different operators. We also find that we have a robust motif, that if we create a combination from constant 1, constant 0, and in the middle another function, it's a good option to use it when we want to do image reduction sequences and pooling for CNN. And this robust motif usually works the best in noisy inputs impulsive, like salt and pepper, and then deeper architectures where the distribution are heterogeneous. And the deploy story is we have an offline step that we have to search which is the best sequences, that it's very expensive computationally. But in other cases, the online step is lightweight operators, because what we have to do is only sort for values and compute 3 simple steps. And the conclusion is that the token function gives adaptive interpretable local aggregation without a full fusing measures, that allows us to have a function with very cheap computationally on 2x2 windows. We do the exotic search, and we found that pattern, the constant 1, another function, and constant 0, and we have a competitive. That pattern is very competitive in both applications, image reduction and the leaves, notably in salt and pepper and CNN pooling. And the next step that we have to in mind is to compute that search in larger windows. But we don't have enough time to do it. And that's all interest.
Thank you very much. So we've got 5 minutes for questions and discussions. Everything is clear? Perfect. Maybe I will ask. If I understood it good, you replace in the standard Shocking integral a fuzzy measure?
Yes.
With some aggregation function?
Yes.
And you erase some values of the vector, yeah, because there are some in the x vector you modify using
yes, we define the x vector, so we choose in each function we take the x values that they are not in the gap. For example, in here, for example, of the function of the first gap, that is the gap between the second value and the first value, we compute here all values except those ones. For example, F1, it was the F1 of X4 and X3. I don't think I the question.
Do you have some theoretical results about the properties of this?
So the properties mostly depends of the function that you choose. Because it depends of the function, you have one properties or not. But in common, you can take properties like monoticity, shift invariance, and that common properties. But it depends on the functions you choose.
And you try to find the best possible combination of function f1 up to f3 in
Yes.
order to get
The
some
properties.
practical results, yeah, because
Yes, so what we do in the first, the main idea of the work is we use image reduction to find the best combination because it's cheaper to find the best sequence in image reduction than in CNN. And with those combinations, we apply them to see to pooling in the CNN to see what's the performance of that 5 best options.
okay. Other question?
X1 and F3, and you variate F2 only, yes, in your
No,
modeling, no?
So we variate the three of them, but in the results we found that the best option, that the best candidates, it's where the one that in the first function is the constant one, and the third function is the constant zero. But we study the all the combinations.
F1 and F3 are somehow fixed, and
Yes,
you variate
it's true. But we study all the combinations. We create a combination. You can see
And-
here you have.
what was the reason to use F1 and F3 of this kind?
The constants. What's the reason?
Has it any
No, what we're try to do is to take very deep diverse functions. We take I don't find no. Here. What we try to do is to search in very diverse candidate pool. So we have a constants, we have a functions from, for example, mean and max, or aggregation function like mean, median, and product, or different kind of we don't have any reason that way we don't those. Like what we try to do is to have a diverse candidate pool.
Hi, thank you for your talk. I know it's not easy that your first talk is the first talk of the conference, so it was a nice job. And my question is about the 2x2 window that cannot be extended to a 3x3 because of computational complexity. So would this exhaustive offline search be improved in some way that if this particular combination doesn't work, then all these family of operators will not work because it's similar to what we do in concept analysis when we try to compute a lattice that we started doing an exhaustive search and then we start to see properties that if this property fails, then you can discard a huge family of operators. So maybe there are some properties that can propose an intelligent search of combinations that could work so that this would be more scalable,
Yes.
not only 2x2, but
Yes.
W by W.
At the first time,
Thank you.
We didn't know what's the performance of the combination will be. So we decided to do an exhaustive offline search because we don't know a priori any knowledge about what will be the performance of that exhaustive, so that each sequence. So we prefer to do an exhaustive search, see its combination, the performance of it, and after that decide if we which is the best one. But as you said, it's true that but with the largest combination, we need to do some other algorithm or heuristic or heuristic to search what is the best combination of exotypes.
Okay, so thank you very much for the discussion. Thank you, the speaker again. And now I'm in a strange situation that I have to introduce myself. So this is the joint work with my PhD student, as well as ideas were from Poland, colleagues from Poland, Polish mathematicians Michał Boczek and Marek Kauszka. So let me briefly introduce what is the idea behind such a complicated thing as I will present. First of all, I am a theoretical mathematician. It means I like proving theorems about properties. I like study new objects, and I do not worry about the applications. So usually the last questions from the audience, and what is it good for? My usual answer is I don't know. So I will do upside down approach, and I will try to explain something which is from practical motivation or practical point of view, and I will try to explain all the ingredients we included it. So on the picture you can see the real record from a smart device of a patient with diabetes. It means that during one day we can see the glucose, how it changed in time, and you can see some specific points, let's say breakfast at 7:30, lunch and dinner. And what is interesting that usually doctors do not take into account values which are 2 hours after the food, and it does not matter how it looks like. The information important for them is somewhere here and there and there. And then after some time, they look at the values of glucose in the blood and decide whether the cure is okay or something should be changed. But if we look at some data from the smart device, we can see that all the values are included. Let's say arithmetic mean is computed because this is in practice it is not a continuous curve because it is valued each 5 minutes during the day. So we have 288 values, and this is in fact not continuous but a discrete situation. And what we want to do instead, daily score should be down weights or some ignoration of glucose values in the first 2 hours after meals. We should focus on relevant times to take some time windows. We would like to allow different aggregation rules on different time segments, not arithmetic mean for the whole data. And the result should be summarized into a single interpretable number somehow. And our suggested setting is as follows. Let us model the daily glucose record as a bounded measurable function. It means we have some time from interval 0 to 24 hours. Let's say we define some post-meal windows as a time set and choose a collection of admissible time segments, let's say 2 hours after or just 1 hour after some meal and so on. Conditional aggregation operator is an object I will explain later. So this aggregation operator encodes how we aggregate on a chosen time segment. So we have an answer to the question, what summary of F, of this glucose record on set E is medically meaningful? Then we take level-dependent measure, which encodes which time segments matter at level T, just answering the question, which time segment should be counted when assessing risk at level T. And the generalized level measure just selects the most relevant segments at some level T, consider all feasible sets such that are greater than the level, and pick one which maximize the importance. And aggregation is Choquet integral. That's all, in fact. Or was that too easy? So if you want to see some mathematics behind, just stay here and stay with me. I will try to explain. So motivations and inspirations from mathematical side are many. The first publication is about Choquet's Stiltius integral. So we would like to modify the measure somehow in the Stiltius sense. This was proved to be interesting tool for decision modeling in 2008. In 2009, a paper level-dependent Sugeno integral appears, which is maybe not so well known, maybe the best known integral and some Stiltius modification of this integral is Choquet one. This paper was published in 2011, and the beginning of the paper is the standard Michel Grabisch example with students and evaluations of the record and so on and so on. The next generalization by means of level-dependent measurables capacities was done for universal integrals. Then interesting paper about Choquet-like integral with respect to level-dependent capacities appeared in 2015. And we entered into this world in 2011 when we tried to understand the situation with level-dependent Boolean capacities and representation of Sugeno integral, as well as more general family of the smallest semicupola-based universal integrals. And then we started a very fruitful collaboration with Polish mathematicians, and we introduced something which is called conditional aggregation operator and a generalized level measure based on this family. So I will try to explain what is the motivation, what are the problems, and where we should be very careful when considering such case. As we all know, Choquet as well as Sugeno integral are nothing but functional which depends on the level measure. The standard level measure, meaning we measure the upper set, the sets of all values for which the function lies above some level. Equivalent expression for the level measure is this formula, which may look quite complicated, but it is true that such an easy object can be rewritten in this not very nice formula. Supremum of all measures of the sets E, which are from the sigma algebra, on which infimum of the function f is greater or equal to a. And now, since we are mathematicians, we can ask the question, what about replacing infimum? Why infimum is so important in this formula? So what about replace infimum with something which is called conditional aggregation operator? It is something which is related to E, set E, and satisfies the condition on this set E. If we have two functions which are comparable on this set E, then aggregation is comparable in the same way. And the second condition, if we have something which produce zero values on the conditioning set E, then aggregation should give the number or value zero. So what about to replace here infimum with a conditional aggregation operator under some convention? This convention is important because if you want to have non-empty set here, then you will have empty set at this condition at each level A. And the second idea is, what about to replace this sigma algebra with a smaller collection of sets? The smaller collection of sets in our case means window which we would like to use in the motivational example. Parameterized system of capacities are known even in the classical integrals. For example, there is a result which describes Sugeno integral as a level-dependent integral with respect to level measure 0,1 Boolean capacity. It was proved in 2018, and then we improved it for the case of not just Sugeno integral, but semicupola-based integrals. Then level-dependent Choquet and Sugeno integrals looks like as these formulas. It means that we consider on each level T, we consider a different measure, which we integrate using the Choquet or Sugeno integral. And for the smallest universal semicupola-based integral, it is also well known that it is nothing but Sugeno integral of vector x, let's say in the discrete case, with respect to me, which is nothing but again level-dependent measure. It is proved in this paper in 2009. So basic ingredients or how to complicate the things. Motivating by stochastic processes, we can consider a process of pavings or some process of collections where each collection contains empty set. And then we define the parametric family of conditional aggregation operators. It means take a conditional aggregation operator on level T, take collection, and all such operators on all such levels should be in this set. And we distinguish several cases of parametric families. It means if the bullet is on the first place, then parameter is here and collection is constant. If the bullet is on the second place, then parameter is on the collection and not on the aggregation side. And if there is no bullet, then it's non-parametric family of conditional aggregation operators. So how such a family may look like. So for example, if we consider a basic three-element space, we consider the sigma algebra. Oh, there's a mistake here, I'm sorry. And the collection which contains just these four sets, then the family of conditional operators may look like on the empty set, there is a product operator. On the singleton, there is a supremum. On the two-element set is a summation. And on the whole, so we have a lot of possibilities on each set and each level. This slide just refers to a generalized level measure, which is nothing but parameterize each ingredients. And if we put standard non-parametric version, then we get back to level-dependent level measure. If we set constant mu here, then we get something like that. And the standard level is possible to obtain using infimum and non-parametric version. So we have a pretty general thing, general object. And now we would like to know properties. Properties should be related to properties of all the ingredients, of course. So the first thing, okay, how can we generate new level-dependent monotone measures? So the standard things, just to recall, take a measure, take some family of functions parameterized by T and apply, you've got a parametric system of measures. Or combination of aggregation and parameter means take aggregation over indicator function multiplied by T, and you get, again, a parametric system of monotone measures. Or the standard thing used by Radko in the theorem describing semicupola-based integral using a Sugano integral is to aggregate value of monotone measure and the parameter t using some aggregation, let's say semicupola and so on. Strange behavior of this object because in the non-parametric case, we have the situation that the map is always non-increasing. It means the level measure is always non-increasing, and the generalized level measure in general is not. There is a maybe complicated example where you can see how it is possible to choose the collection, how it is possible to choose the system of parametric measures, and how it is possible to choose the system of aggregation operators. And that's the result. We can see that it is not non-increasing, so we should be very careful when considering measurability, for example, because this function need not be Borel measurable and therefore need not be Lebesgue integrable. So if we want to know something about integration with respect to such strange thing, we should be very careful. So this example is from this paper that even in the case of finite set, we are not in the position that we can guarantee Borel measurability of level-dependent level measure. And of course, many questions appear. What are the properties with respect to gradients? So there are some very trivial properties. It is always monotone with respect to function, with respect to measure. Of course, we should define what does it mean that the system of measure is less or equal to the system of other measures. And the next ingredient is a family of conditional aggregation operators parameterized by everything. So it is also possible to prove that it is monotone with respect to such family, and several elementary properties are related to how can we write this parametric formula for some specific values, and this was done in our paper in 2023. Okay, so the first question, do we know something if we replace infimum with some other aggregation operator, how these two objects are related? So the first answer is, when does the equality appear? So when we obtain the standard level-dependent level measure, the answer is here. In the case of trivial sigma algebra, it is possible if and only if the aggregation on the whole X is idempotent. And if we take a non-trivial sigma algebra, then this equality holds if and only if we get infimum. So in fact, if we replace infimum with another aggregation operator, we will never get the standard situation. So there is a whole place for doing mathematics and try to prove some properties, and it looks complicated. I know. So there is just one small example of a proposition for super additivity, because this property is important when we want to integrate, because the integral will not be additive, so at least super additive and so on. And there are some properties which should be included to this proposition. Of course, it is not a necessary and sufficient condition, just sufficient. And what about complication with Choquet integral? And we would like to include some measure. The standard Lebesgue-Stieltjes integral is built on in such a phi measure, and how integrals may look like. So, for example, such a functional is very strange, but it is quite natural if we restrict this operation L to such an easy formula. Then we get the main object Choquet is type integral of functional. If we replace the L function with such a things and infimum operator, then we get the standard level dependent Choquet integral of Greco, and and Narukawa-Murofushi properties, and we can continue try to understand what are the properties of such a strange functional, and there are some which I will not comment because this is a work in progress, and we would like to find a characterization of each property related to properties of all the ingredients included here. Now for real, it is real for this time. Thank you for attention. Okay, so now there's a short time for questions.
I have no question. I have only small comment. Maybe it looks strange that our paper on level dependent Sugeno integral appeared in 2009 and Choquet integral based on level dependent measures due to Giove, Salvatore Greco, and Materazzi 2 years later. In fact, they were the first, and they have presented this idea in 2007 at written seminar. And when they have submitted this paper with application in decision making for a real example. But the problem was that a referee have commented that first part related to theory, it's perfect, it's okay. Second part with decision problems, and so they had some problems. So they have proposed them to split these two papers, but they were fighting for having it in one paper. Therefore, it takes longer time. And though we were continuing their ideas from Sugeno integral, but our paper was published earlier. So if you want always to stress this idea when it appeared in integrals, so this is idea of Salvatore Greco and these two co-authors.
So we do not have a time for the next question, so I hope we can discuss later. Thank you very much. And the next speaker, the last speaker in this session number 1 is Tomasz Józefiak from the School of Polish Mathematician in Łódź.
And many thanks. Hello, everybody. So my name is Tomasz Józefiak, and I would like to speak about the work that I did together with Marek Kołuszka and Andrzej Okolewski. And also many thanks to Andrzej and to Michał Boczek for the ideas for this presentation. So let me start with motivation behind all of that. And for that, we have to move a little back in time. In fact, we will be moving back in time to the year 1980, where the paper regarding the prospect theory was established. And actually, he received the Kahneman and Tversky, they both did it. And he received for that the Nobel Prize in economics. And this second paper is actually one of the most cited papers ever in the economy. And it is relatively simple, but the idea is great in that. So basically, let me ask you the question. Would you like to have 1 million euro right now, or flip a fair coin? And if the tails falls up, then you get 100 million. It's a hard question because 1 million is already the money that can change the life. And they kind of did this experiment with many questions like that through the representative group of people. And they have established that in general, this is how the utility function of the gains or losses looks like. So yeah, this says that people are not in general willing to lose the money, and they are kind of they have the risk aversion, and yeah, this is the concavity, and as we can see over there. However, there is also an idea that derives from that in general we should use the different later on monotone measures, which would differently aggregate both positive values and different negative values. And therefore, as we already know the definition of the Shortcut integral here is in the continuous case. It later on became very useful to use two different monotone measures, me and to differently aggregate the positive and the negative values of the function. And it was later on developed in many, many ways, especially taking into consideration the discrete space X. But in 2024, we have published the paper on an extension of the Shortcut integral for multi-valued data, where basically we wanted here to have not only one function, but to have two functions, three functions, and so on. In general, n functions, because yeah, for example, the Riemann integral, we can have the double Riemann integral and so on, which would return the single value as an output. So how did we proceed with it? We proceeded with it in the following way. This is the general formula. And this is the part which is for all of the non-negative functions. So the basic idea from that is that we are here using the different measures for if the product of these functions would be positive or would be negative. It's very not very complicated, but some technical things are there. So let's look how it looks like for some certain numbers n. So if n equals to 1, we recover the standard shortcut integral for two monotone measures. And this is what I would like to focus on right now. What happens if n equals 2? So this is what I meant by having to differently aggregate the both positive and negative parts, where each of this component is derived from that formula. So we can see also here we are adding the operator AND. So we are taking into consideration these elements which satisfies both of these conditions. So f of x bigger than t1 and f2 bigger than t2. And this can be the Lebesgue integral or the Riemann. We chose the Lebesgue because of some properties that we later on proved. But under some circumstances, it doesn't really matter which integral we choose. Also, it doesn't matter if it is bigger or bigger equal. Okay, so we have a tool. We have the CH Shortcut integral for many functions. And yeah, we proved a few theorems for that, which are pretty good, but we would not focus on it today. I would recall looking at this paper if you want to have some more technical background to it and see the properties. The title is of my presentation, Variance Functionals. So how can we, from that, get the variance? Because we know that the Shortcut integral generalizes the standard expected value. So in this way, we would like to somehow get the variance functional, which would generalize to the case of the monotone measures, the standard variance for the probability. So people already did something like that. For example, Sugeno or Jager. And they kind of considered the case only for the one monotone measure, and it looked something like this. But this we can actually even more expand, considering, as you can see, two monotone measures. So these ideas of this three variance functional derive kind of from their work, but also utilizing the concept of having two monotone measures. Okay, but I introduced at the beginning the concept of the double Shochet integral. So how can we go with that? The answer is on this slide. So let's take a brief moment and see what is happening here. So here is the concept of the double Shochet integral in this definition. We can use the simply one monotone measure, because if this is the same function, then it doesn't really matter what we put next to it. And at the V5, here is where it is the concept of the double Shochet integral, because we are using here the dot, meaning the comma, meaning that here would be the definition of the double Shochet integral employed. So, okay, now we have some definitions of the variance, but how do we do now? What do we do, and why would it be helpful? So the remark 3 says that all of them are different, meaning that we get why we introduced a few of them, not only one of them. And the remark number 4 comes back to the, let's say, the idea behind the Shochet integral, that in the case of the probability theory, it generalizes the expected value. And here we can see how this generalizes the variance. All of them become the standard probability variance if we are dealing with the same probability measure here. Okay, so right now we know that it is indeed some kind of extension. We know how it works. We know the definition. We know why we needed the concept of the double Shochet integral. We know why and how we introduced the idea of differently aggregating the positives and the negative parts of the product of the functions. So let's see the properties of this variance functions. So this property that the variance of the single scalar equals 0 is satisfied for all of them. Okay, this is good, because this also holds for the standard variance. The non-negativity is satisfied only for the for the formula 2, 3, and 5, and under some circumstances also for the V4. And let me recall once again that V5 and V4 were the definitions where we indeed we used the concept of the double Shochet integral. And some other properties would be the invariance due to the adding of the scalar, which holds only for the non-negative functions and non-negative scalars. And it does make sense if we come back and think that we use the different measure to aggregate the positive and the negative parts. So we actually would not want it to be satisfied for all of the functions and for all of the scalars. The same as the linearity in the square property. It is satisfied only for the positive A. Okay, so now we know the definitions, we know the properties. So let's see how does it reflect the idea of the variance and where it will be utilized, and what are these connections to the literature. I think it stopped working. So in the same way as we introduce the various functions, we can introduce the covariance in two different ways. And yeah, having that, we can simply use it to solve the well-known Markowitz model for choosing the portfolio, which would have the low total variance. And the total variance would be used by this covariance matrix, which we can get, for example, from the prices of some actions choosing the portfolio. And, under some circumstances, it would always have the solution. Sometimes it would be only one solution, sometimes many of them, depending on the matrix of the covariance of this rate of returns over the process. Another thing is, just I know many of you work with a discrete space. So if we are dealing with a discrete space, then this part of the function, the variance, which is the double shooted integral, looks like this. And actually something like that has been done in 2023, where it was the paper entitled the Deriving Efficiency from UV. And basically we can interpret this as, if we want to aggregate the function f, having some assessments of the experts, for example. How do they believe, what is they believe that indeed the value of f is obtained over this x. Another very important thing is that if you want to find the average value of something, so of course we can use some average function, but the general idea is that having some function, the average should satisfy this solution. And we have proven that it would always have at least one solution. And yeah, average value, many applications where it can be chosen. Also, there is some way of dealing with it, maybe from the Sugano's work, which would allow us to directly compute the value if we are dealing with this Lebesgue measure as a limited measure for the. So we can have a direct formula to calculate this. So it also goes almost without saying to the concept of that. And I would say if you think that in your box you potentially use the variance in terms of the Chopin integral simply is some measure of dispersion of the function. And for example, it can be used in the where you have some classifier rules to just have another, let's say, assumption or the information that should be satisfied in terms of the variance formula and covariance. It can be also utilized over there. And I think that 2 years from now, I would have the presentation where I would show you how are the advancements in the application of this model. And actually, I'm looking forward because I started some kind of cooperation where we created the algorithm for choosing the best ski for the skiers based on their g-forces, which are derived from their onslaught data. And I hope that here it will can be used. But if you have any other idea, please feel free to contact and to cooperate. It's all from my side. Many thanks.